So for this sessions, 2.9 is linear approximations, because basically from the previous session, the last problem, when I illustrate with the picture, right, you can see that this tangent line can be basically like, close to approximating the actual function value. So 2.9 is basically talk about linear approximations, and it go into further into talking about differentials, which will help us to approximate a little bit easier and better, smoother. The first thing that I wanted to talk about is like, changing, fixing my mistake, my typo on the printing. So notice that right here, the linear approximations, I make a typo right here. So make sure you cross it out, and then the equation should be f of a plus f prime of a times with x minus a, which is the equation of the tangent line. Okay. So to start it off with, this is like, what we already know. Let's say I have a functions f of x, right? And we want to find out the tangent line at a point A on the functions, right? So when x is equal to a right here, so therefore my function value will be f of a at this point. So we know that derivative of the functions evaluating at that point, that basically going to give me the slope of the tangent line. So you can see that, the point a and f of a with the slope of the tangent line, when I put it into point slope formula, that give me y minus f of a is equal to f prime of a times with x minus a. So by adding f of a to both sides, now I got y is equal to f of a plus f prime of a times with x minus a. So that basically tells me the equation of this tangent line already. Okay. So we already know that the function value of the tangent line and the function value of this f functions at a point A, they are both the same. But what we are interested in is like using this tangent line function, right, to approximate the function value on f at a different points. And of course, these approximations will be very, close approximations if the value that we are approximating, x is close to a, in the neighborhood of a. Right? So therefore, we can see that the next things that I talk about is linear approximations of the functions at a, that means around a. This function value can be approximated with the value of the tangent line. Okay? And this equation right here, the equation of the tangent line that we got, we can talk about this as, give us as a name, linearizations of f at a. So we would denote it as L of a. Now we're going to be talking about the tangent line as a function of x. So basically what it's saying is like, as you can see, if I'm talking about my x is right here, and then my value on the tangent line is right there, but the actual value of the function is right here. So you can see that the gap is big right there, right? So the approximation is like, it will be more error. But as we talk about this x is very close to a, right, of this tangent line that we found out. And then you can see that the function value and then the value on the tangent line are very, close together, so that your approximation will be very close. So that's what basically it is talking about right here. Okay. So now, before I continue, right, is there any questions on this introductory part?
The recording has stopped.
Are we all okay with this? You understood my point right here?
Could you actually do it in more plain speak?
What do you mean by plain speak?
Just like, how is this different from the other stuff we've done before in this chapter?
Oh, the other stuff that we talked about before never talk about approximations at all.
Okay.
Remember, we are talking about, the other sections, we are basically looking at what? Exact value, taking derivative and then finding out a particular, evaluating, right, a particular value of the derivatives.
Right.
But this one is basically talking about right here. If I have a function, if I know the tangent lines right here, right? The functions right there. But tangent line is basically based off on a particular point. But what this linear approximation is talking about is, hey, if I can use the function of the tangent line to approximate the function value of f at this particular point, x.
Mm-hmm.
That's what basically this, the linearization function is talking about. But however, you can see that as the value of x is far away from a, then you can see that the gap is bigger and bigger.
Yeah.
So therefore, this linear, of course, a linear approximation only works, and works well or approximate well when you are talking about the value of x is close to what? That letter a right there. Of course, if you want to approximate right here, this value, I want to maybe try to find out the linearization functions around right here, right? Linearization functions around right here, so that it will help me to approximate better with this linearization functions rather than this first one that we found.
Okay.
Does it make sense?
Mm-hmm.
Are we all okay with this, the rest of us? And that's the problem with this linearizations, functions right here. Okay, because if it is far away, it's not going to be really good approximation. So the next thing that we're going to talk about, the differential, is basically help us to get better approximations. Okay. So if we are okay with that, then I'm going to move on to the examples. Okay. Mm-hmm. So taking a look at the first example.
This meeting is being recorded.
So example 1 is basically asking us to find the linearizations function, and then of the functions f equal to cube root of x at a particular point when x is equal to 8. So first question is find out the linearization function first for this particular function f, and then after that we use the linear approximations to approximate the value cube root of 8.05 and cube root of 25. So to find out the linearization functions, right? And what is the key thing that we need? We need to know the derivatives of the functions evaluating at that particular point, because that's basically referring to the slope of the tangent line at that particular point. Because remember, linearization function is basically a fancy name for equation of the tangent line. So now, first, my functions f of x, that is equal to x to the 1/3 power. So therefore, when I take derivatives with respect to x of these functions, which will become 1/3 x to the negative 2/3 power, which give us, simplifying a little bit, that will be 1/3 times cube root of x squared. So to find this linearization functions, first I need the point. So what is the function value at 8? That is basically cube root of 8, which is equal to 2. And what is the slope of the tangent line at 8, right? Which is going to be f prime of 8. That will be equal to 1/3 times cube root of 8 squared. So which is going to be 4 times 3 is 1 over 12. Now, put it into linearization function, which is L of x, that is equal to f of 8 plus f prime of 8 times with x minus 8. So this gives me f of 8 that is equal to 2 plus 1 over 12 times x minus 8. So simplifying a little bit further, that will give me 1 over 12x. Multiplying 112 times 8 is 2/3, and then 2/3 minus 2/3 plus 2, that will give me plus 4/3. So this is the linearization functions for this particular functions at that point. So the approximation will work well when x is close to 8, and we're going to find that out very soon. So why? Because this is the first part of the question that's asking, and the second part of the question is asking you to approximate, right, to do the linear approximation for cube root of 8.05. So that's basically talking about looking for the function value of 8.05, which is, when we do the linearization, linear approximation, this is basically approximately equal to linearization functions evaluating at 8.05. So this gives us 1 over 12 times with 8 plus 4 over 3, and which will give us approximate answer when you use a calculator. Okay? And this will give us 2.00416667 ... Right? Let's continue on. So we got approximations already right here, right? That's the linear approximations. Now what I want you to do is compute the actual value. What is the actual value? Which is cube root of 8.05. What do you get when you compute it? Okay. Scientific. Okay. So 8.05 to the power of 1/3. Oh no, this is not right. But anyway, you got your answer already? It should be close. Okay. So if you continue on the next one, function value evaluating at 25, which is cube root of 25. If I use the linearizations functions evaluating at 25, and this will be 1 over 12 times 25 plus 4 over 3. And this will give us approximate answer 3.14666667. But if you actually use the calculator and then compute cube root of 25, and you will be seeing that this answer, approximation answer, and the actual answers have a big difference. Right? A big difference right there. And that's predictable, right, from the introduction that I'm talking about earlier, because this linear approximation works well on around x equal to 8. But 25 is very far away from 8, so therefore, the approximation will be off. So